Welcome to the Professor's DuBois channel. This is Professor Corey, and what I'm doing here is a little mini lecture from our final lecture on Chapter 11, where we tackle a couple of problems. And what really makes these problems, I think, challenging is that we have to bring back our ideal gas law, or our combined gas law, in order to solve them. And this is from Chapter 10, which seems like a long time ago. But I'm just going to kind of walk through one of these to kind of help you through it. Now, the problem here, we have a vapor pressure, like the first line, and I broke it out here because this is really, it's like the law. The vapor pressure of liquid bromoethane is 100 millimeters mercury at 263 Kelvin. That's a fact. That won't change unless the temperature changes. So if we have some liquid in a container, the vapor pressure above that liquid is going to be 100 millimeters mercury as long as we're at 263 Kelvin. It doesn't matter how big the container is, how much surface area, how much head space. If we have liquid bromoethane in any sealed container, the pressure can only be 100 millimeters mercury. Well, what if we evaporated? What if we had some liquid bromoethane and it all evaporated? Well, our pressure would have to be less than 100 millimeters mercury. Once we get to 100, we reach the equilibrium where we'll get condensation instead of going above 100. So what we're looking for in these problems oftentimes is, what will the pressure be in the container? And we'll have a set of conditions. Now, this one, we have a mass of this liquid bromoethane, and we have a volume, and we have a temperature. And the question is all of this mass of bromoethane going to evaporate? And then they want to know what the pressure will be when the equilibrium is reached. Now, realize, I'll say this so many times, the pressure cannot be higher than 100 millimeters mercury at 263. Instead of going higher, we'll get condensation. So when we use the ideal gas law, we can use this and we can calculate a pressure. Now this pressure, it's just a theoretical pressure. If we have a volume, an amount, moles, and a temperature, this is like the theoretical pressure. But the ideal gas law doesn't know what gas we're talking about, and it doesn't know anything about vapor pressure. It's just given us a theoretical value. So we need both parts here. We need to know what the vapor pressure is, and we need the ideal gas law to solve this problem. So what I've done here is I didn't do the workout. I'm just going to kind of talk through this. You should be able to do this. We're using PV equals nRT. And what I did is I rearranged the equation, and I just divided both sides by the volume. So I have P equals nRT over V. So the number of moles, we took the grams of bromoethane in the molar mass, and I have 3.2853 times 10 to the negative 3 moles of my bromoethane. That's N. R is the ideal gas law constant. That's 0.082057. Units on that are liter atmosphere per mole Kelvin. Now I can tell right away my pressure is going to end up in atmospheres. I'm going to have to do a conversion, but that's okay. We'll deal with that later. Lastly, my temperature is 263 Kelvin. The volume here, we need that to be in liters. So I just converted the 380 milliliters to liters at 0.380. Now when I solve for the pressure, I get an answer in atmospheres, and I got 0.187 atmospheres. Hopefully I did this right. And when I convert that to millimeters mercury using the conversion factor, 1 atmosphere equals 760 millimeters mercury, I get 142 millimeters mercury. So you should try to work through that. You should be able to do that on your own and get 142 millimeters mercury. And now we have to stop and think. So that is a theoretical pressure if every bit of this material went to the gas phase. Now, however, the vapor pressure is 100 millimeters mercury, so we can't get to 142. What this means is that our pressure is going to be 100 millimeters mercury, and we're going to have liquid present. The extra liquid is not going to it's not going to completely evaporate. It's going to condense, so we'll have liquid with a pressure of 100 millimeters mercury. Another question that is similar is we get, the same thing. They write in at the start, the vapor pressure is this at this temperature. This is the law. This is the vapor pressure of liquid ethanol at this temperature. It won't change. So as long as we have liquid, we have a vapor pressure of 100 millimeters mercury at 308 Kelvin. Now, in this question, they've got a sample, and they didn't tell us how much the sample is, so I can't calculate the moles like before. So it just says a sample of ethanol. It's in a closed, evacuated container, so there's no pressure in this container. We're starting out with in a vacuum, and we've got the volume of the container, we've got the temperature, and we found that all the ethanol is in the vapor phase and the pressure is 50 millimeters mercury. And this makes sense because we know that if there was liquid ethanol present, the vapor pressure would be 100 millimeters mercury. Our pressure is not 100, it's only 50. We must be in the gas phase. And now what they're saying is, all right, well, what if we took this container and we made it smaller? So we have the same amount, but now we have a smaller container. So reducing the size of the container would increase the pressure. Well, we need to solve for the new pressure, and then we can make some statements. So the way we're going to do this is we're going to use the combined gas law, and we can write that as P1V1 over T1 equals P2V2 over T2. Now in this case, the temperature is constant. It's at 308 K throughout. So I can just eliminate the temperatures and say P1V1 equals P2V2, or I could put the temperature in. It doesn't matter. I usually choose to leave it out. So I have, for my P1, I'm going to use 50 millimeters mercury, and my V1 is going to be 584 milliliters. Now I could have assigned this P2 and V2. It really doesn't matter, but I chose P1, V1 to be 50 and 584. P2 is what I'm going to solve for, and V2 is 367 mils. So when I solve for this, I get 80 millimeters mercury. What this means is that the pressure in this container, the 367 mil container, is 80 millimeters mercury. And that's okay because it's not above 100. It can't be above 100. So since it's below 100, what that means is we're in the vapor phase. There's no liquid present. So again, I can't say this enough. If we have liquid present ethanol in any size, shape, container, we'll have a vapor pressure of 100 millimeters mercury at that temperature, 308 K. So in this case, we have a pressure that's lower than that. So what that means is we don't have any liquid present. We're still in the vapor phase, and we do have a higher pressure as expected. So that's fine. These questions, a lot of times they're like select all that apply. And so that the key things are, in this instance, we don't have any liquid present. We're all in the vapor phase. The pressure is 80 millimeters mercury. So a little practice goes a long way with these. You'll warm right up to the combined gas law and the ideal gas law, just like you did in Chem 111. So hopefully you found this useful. If you did, please give the video a thumbs up. I'd love to see that. And please keep watching videos, mini lectures from the Professor's DuBois.